Hi, I'm Pietro and I will be talking about black start and fault-tolerant operation of an isolated single-stage DC-AC converter for DC microgrids. There are a number of ways of achieving isolated DC-AC conversion. The simplest way is to have a non-isolated DC-AC converter followed by a line frequency transformer, such as this one. Of course, line frequency transformers are very large and heavy. The conventional solution is to instead use a isolated DC converter with a high frequency transformer, such as this one, which has the same power rating, followed by a DC-AC conversion stage. However, as there are two power conversion stages, a DC link is required to decouple these two power stages, and this DC link is usually composed of electrolytic capacitors, which are large, heavy, and expensive. Also, there are a reliability issue as their operating lifespans are quite short. Alternatively, there is an emerging single-stage solution that directly converts DC to AC with the isolation of a high-frequency transformer and no requirement of a DC link, and so no electrolytic capacitors. This work is about studying the capabilities of this converter under transient conditions such as startup and fault.
This is a 3D model of the converter. The grid-connected inductors feed a sinusoidal input current at grid frequency into a 3x1 matrix converter, which steps up the frequency to high frequency, fed into a high-frequency transformer that is then rectified by a full bridge that is connected to the DC microgrid. The problem of soft start lies in the DC microgrid capacitance. When it is discharged, it acts as a short circuit and can draw large inrush currents that can damage equipment. To address the soft start problem, it's possible to exploit the bidirectional switches of the matrix converter to create controlled current pulses that charge the DC microgrid. So these are some simulation results, and this is the current the current pulses that are generated, and this is the voltage of the DC microgrid that is slowly being charged up to. In the case of grid under voltage, as this is a boost-derived topology with the inductors on the grid side, it's possible to boost the grid voltages to maintain the DC bus voltage. Finally, in the case of the loss of a phase because of bad cabling or whatever reason, the converter can be reconfigured to operate off of a single line-to-line voltage, and in that case it essentially becomes this topology. So here are some simulation results. When the phase is lost and it operates off of a single line-to-line voltage, a 100 Hz ripple is introduced near the zero crossing, and the nominal power is decreased, but the converter can continue to operate. That's everything. Thank you to the IEEE IES Students and Young Professionals Association.